So, talking about intensity. The word intense or intensity, what does it immediately tell you? Intense, like more, right? Now, we are talking about intensity of sound or intensity of waves. So if there is more energy involved, then that must be intense. Okay, that musical instrument is played in a very intense manner. You know, the sound is so intense, which means it's too loud. So intensity is a kind of measurement of energy, but it's not measurement of just energy, but energy per second. So to give you an example, if I'm going to talk with a certain power right now, if I'm talking with a certain power, like 100 watts, what do you mean by 100 watts? What do you mean by 100 watts? 100 joules per second. So every second, when I'm talking, every second it's 100 joules of energy. How much of that is heard by you? Are you able to hear all the 100?
No.
No? Why?
Because it has to also push the air.
Yeah, it is pushing the air, but 100 has to come out, right? The 100 has to be in the air. My question is, are you intercepting my 100 joules? Why not?
Is your voice?
My voice could be going everywhere. You are only intercepting a tiny, tiny part of it. Your eardrum is what is the size of the eardrum? That is the only part which is intercepting my voice. The rest is gone. The rest is going through. And so, and also the other thing is, the closer you are, you're going to intercept more, right? The closer the same eardrum is, you're going to intercept more. And so how do we measure intensity is by this. So let me give you an example. Let's say there are 100 people in a field. There are 100 people in a field, okay? And all the 100 people are going to be dismissed from that field. But there's a boundary wall. This is the boundary wall. And I built another boundary wall here. And I built another boundary wall here. And I built another boundary wall here. So there are many boundary walls. If 100 people are dismissed from here and they're supposed to be going away, how many people are jumping across this wall? How many should be crossing? 100, all of them. How many will be crossing this boundary wall? All the 100. How many should be crossing this boundary wall? 100. And over here? 100. All the 100 have to cross. But what's the difference between the crossings?
Spread out.
If I look at 1 meter distance on the, so the wall is like 1 meter. If I look at 1 meter of this wall, so many will be jumping at the same spot, right? Whereas over here, lesser. And over here, lesser. And over here, further less. The reason? Because there's a lot of, total length of the wall is too much. And therefore, not everybody need not jump through the same spot. They will be spread out. That means the intensity of jumping is here, maximum, right? Less intense, more intense. That's exactly how we measure sound. Now, sound is not going to go in a circular manner. When I talk, the sound is going in which manner? Spherically. Spherically. So the boundary wall is not a circle, it's a sphere. The boundary wall is a sphere. So if I want to know the intensity over there, the intensity is defined as energy per second per unit area. So if I take 1 meter square area, how much energy per second is passing through that? That is how we measure the intensity. Like for example, if P is the number of joules per second that's going out, it's the same P that's going out everywhere. The P over here, the total energy of P is going through an area. What's the surface area of a sphere?
Pi r.
Sphere.
4/3.
4/3 pi r cubed is the volume of a sphere. What's the surface area of a sphere? Anyone? You should know it. ACT or 4 pi r squared. So 4 pi r squared. So this is the amount of energy per second that's going through 4 pi r square area. So how much is the energy going through 1 meter square? How much? If P is the energy per second going through 4 pi r square, what is the energy going through 1 meter square? If P is the energy going through all this area through 1 meter square, how much? Okay, if if you get P number of cakes for $10, for $1, how many cakes? P divided by 10. Now tell me in terms. If P cakes you can get 4 pi r square dollars, and for $1 how much? That is the intensity. Through 1 meter square, how much energy goes through? That's called intensity. So intensity I is equal to P divided by 4 pi r squared. And intensity, what's the unit of intensity? What's the unit of this? Watts. And what is this one's unit? That's it. So watt per meter square, that's a unit of intensity. So how do we measure the intensity of my talking at James's location? He is at a certain distance. So to know exactly the intensity there, this is my power, 100 watts, divided by 4 pi times the distance squared. Because he is intercepting that area, right? So power over 4 pi r squared, so you can measure that. Now Nick is sitting 5 meters away. Let's say James is sitting 1 meter away, and Nick is sitting 5 meters away. So how much will be the intensity at his location? Remember, this is getting squared. So for him, I'll put 1 over here, so 1 square is 1. For him, I'll put 5 over here, so 5 square is? So how many times, so how much intensity is he getting compared to James? 1 over?
What? No, never mind.
1 over what? Like if he's getting certain intensity I, what is the intensity that's coming to your location? 1 over 25th of what he's getting.
Oh,
You understand this? This inverse square. Intensity is inversely proportional to square of the distance. So if I double the distance, the intensity is going to come down 4 times. If I triple the distance, the intensity is going to go down 9 times. Now the distance is 5 times more, so the intensity goes down 25 times. So the intensity what Nick is hearing is 25 times lower than what he's hearing. But in this room, that is not true. Why?
Diffraction.
Walls, reflection, diffraction, refraction, anything. Because of the walls, the sound is reaching him by all manners, reaching him by all manners. And therefore, the intensity at his location and at that location is literally the same. Not big difference. He may be having a little advantage, but Nick is getting almost the same number. So wherever you sit in the room, it's going to be almost the same intensity. But if I repeat this in an open field like a desert, imagine I'm standing at a desert and there are students standing at different points. One is there, one is there. And if I talk, the one who's further away will get very little of what I say because there's nothing to reflect. You get it? So this calculation will go perfectly well if there is no reflecting surface. So intensity is measured in terms of this equation power of 4 pi r squared. So same thing with light. Light also, so intensity is something that is used for all waves. The brightness, look at the brightness here. See? Can you see the brightness here? What will happen if I take this paper from here to halfway up?
Brighter.
How many times brighter?
2 times.
4 times brighter. You can see this from this location. If I take it there, has it become brighter? It's actually 4 times brighter. So by just changing from one spot to another spot, it becomes brighter by that many factors. So if I halve the distance, it's going to be 4 times bigger. The closer you go, more. That's what intensity, and its unit is watt per meter square. And if you really want to know how much is the energy per second that's coming into your ears, what you need is 2 things. Intensity at your location and how much area you are intercepting. If you know the area of your eardrums and you know the intensity, multiply them together, you get the energy per second, the power that's coming into your ears. Okay? And although intensity is measured in watt per meter square, we use different units for intensities. So let me give you some sample numbers for intensities. Now, there is something called threshold of hearing. Threshold of hearing is 1 times 10 to the power of negative 12 watt per meter square. This is for a normal human being. It's 1 times 10 to the power of negative 12 watt per meter square. So if the intensity that you're hearing, is that or more, you will say, yes, I can hear it. Do you hear the sound?
No.
If you're not hearing the sound, that's because the intensity of the sound at your location is lower than that. Now I hear it. I couldn't hear it here because the intensity was lower. But when I brought it closer, it is giving out sound. Okay, so it looks like there's no sound at all from your location, but if I come straight to you, closer and closer, the intensity gets better and better. Do you hear sound? It is still making the sound, but the thing is, so is this sound reaching you? Yes, it is reaching you, but you can't sense it because that's a threshold of hearing. That's a threshold of hearing. I'll give you some numbers here so you will have an idea. Rustling of leaves, like, that when the leaves kind of roll over each other, rustling of leaves is like 10 to the power of negative 11 watt per meter square. This is rustling of leaves. Whispering, when someone whispers, is like 10 to the power of negative 10.
Wait, but doesn't it depend on
It depends on the proximity, depends on the distance. But when someone is whispering, like close to him, see, I'm not writing the number in front, I'm just writing only the power, the order of magnitude. So it's 10 power negative 10 is for whispering, when someone's, that sort of sound. Quiet radio is 10 power of negative 8. This is the radio. Not blaring too loud, but normal radio. Talking from 50 centimeters. When someone is talking and you stand 50 centimeters away, then it is 10 power negative 6. That is the this is the energy per second per meter square. Busy street traffic, 10 power minus 5. That's busy street traffic. And inside your car interior is also 10 power minus 5. Inside your car, it's almost the same as standing next to the busy street. That's the same intensity. A siren at 30 meters. And I say 30 meters, like from here to student affairs. If a siren goes off as the student affairs, it is like 10 power negative 2 intensity. Loud rock concert. Is one. There's a loud rock concert. Threshold of pain. Is 1 watt per meter square. What does it mean? What does it mean? The loud rock concert is painful. If you are standing right next to all those big speaker systems, you are really on the verge of saying, oh, it's painful. Why is it painful? Because the eardrums are stretching too far. The intensity, the amplitude is too much that the eardrums are stretching too far, now it can tear. It can tear. Anything more than that, it's because the pain is an indication that you are exceeding limits. And what happens after that is tear. The eardrums can tear, rupture. A jet plane, 30 meters is like 100. Like imagine there's a jet engine near the student affairs and you're standing that distance away. And when it starts like full speed, the engines are on, standing here without protection, the eardrums will be done. It's such a lot of sound that it can tear your eardrums. So people who work in those areas, they'll always have protections. You don't want to stand at places like that. So you can see the intensity is really high. Questions? So you can see how the intensities change. This is a threshold of hearing. This is what is minimum required for you to say, yes, I can hear. And this is the threshold of pain. You don't want to go more than this. This itself is too much. Like the fire alarm when you're actually standing next to it, it's pretty loud. This is siren at 30 meters. Now the closer you go, it is approaching this. So the fire alarm could be very close to this one. And that can be bad for the ears if you're actually subjected to it when it's too close. Now intensities are these, but we don't measure intensities using this unit, which is watt per meter square. For a better comparison, we always compare with this number, which is, this is what I need to hear. And this is what I'm hearing. And therefore you compare it that way. And so to compare intensities, we use this equation. Intensity is 10 times log of intensity over intensity naught. It's a logarithmic scale. The comparison is done using a logarithmic scale. Now, because we're using the number 10, that's why it is called deci. And the whole thing is measured in decibel, dB. So sound is measured in decibel. The D stands for deci. How many decimeters are there in this? 10. That's why the number 10. This 1 meter is split into 10 decimeters. The same way 1 bell is split. Yes.
What is the I?
I stands for the intensity that you're comparing, and I naught is a threshold. That is the threshold of hearing. So what is the intensity for the threshold of hearing? For the threshold of hearing, what's the intensity? So what is the intensity when you can say, yes, I barely hear it? Then you do this calculation, 10 times log 10 to the power of negative 12 over 10 to the power of negative 12. So what is What is 10 power negative 12 over 10 power negative 12? Log of 1. What's log 1? 0. You must have done some log, so you should be knowing log 1 is 0. So log 1 is 0, so the whole thing becomes 0 decibel. So this is the intensity that is threshold of hearing. This is the intensity that you can say threshold of hearing. So 0 decibel is the beginning of hearing. Now on the basis of this, what about talking? When someone talks to you from 50 centimeters is this much. When someone stands that close and talks to you, just normal talking, not screaming, it's 10 power negative 6, right? For talking. So the intensity of talking will be 10 log 10 to the power of negative 6 over 10 power negative 12. And so this becomes 10 log 10 power 6. And when you do log of 10 power 6, the 6 will come down here, right? You know the power rule for the logs? Log of 10 power 6, the 6 will come down here, so it will become 10 times 6 log 10. What is log 10? 1. And so it becomes 60 dB. So this is for normal talking. This is for barely hearing it. What about threshold of pain? What's for threshold of pain? For threshold of pain is 10 log. 10 log, what is the threshold of pain? 1. This is 1 over 10 to the power of negative 12, which is 10 log 10 power 12, which is 120 dB. That's pain. So as long as you don't cross that, between 0 and 120 dB, you are able to hear things. Above 120 dB, you're going to damage your eardrum. The talking is this one, 60 dB. So you can see how the intensities are compared. So instead of using watt per meter square, you can always use this for comparison. It's easier, right? Instead of using all the 10 power negative 12, 10 power negative 8, instead of that you can say 0, 10, 20, 10, 20, 30, 40, 50, 60. That's easier to compare. You can always have 65, 66, 67 dB. So the numbers from 0 to 120 and all that is easier to compare and all that. So if you're talking about jet plane, what's the jet plane's intensity? 140. It'll be 140 dB. So this is what is causing pain, and 140 dB is the jet engine's intensity. Any questions on this? The next thing is about resonance in tubes. Resonances in tubes. Now, you've seen resonances in a string, right? When a string is plucked, you saw the resonances, overtones and all that. The same way, you can have resonances in tubes. Now, tubes, there are two types of tubes. You have two types of tubes. Closed tube and then we have an open tube. So this is a closed tube. What's a closed tube? It's a tube that is closed at one end and open at the other. It's a tube that is closed at one end and open at the other. That's why it's called a closed tube. And what is an open tube? An open tube is a tube that's open at both ends. Open tube is a tube that is open at both ends. And closed tube is closed now, closed at one end. Now what happens to a closed tube? So this is a closed tube. Can you see this pen cap? And I've already shown you this demo. That's a pen cap. That's closed here, open here. So when you disturb the top part of it, what happens? Longitudinal waves go down, then bounce back up to form a what kind of wave is formed inside? Standing wave. Just like in a string. Sound waves, longitudinal sound waves goes down, bounces, comes back to form a standing wave. And the standing wave that you form in a very basic manner, basic formation, that's called fundamental, right? I woke you up.
I wasn't asleep.
No. All right, so sound that you're hearing right now is the fundamental. So what exactly is happening in the fundamental? So, all right, one more thing you should understand is any open end has to be an antinode. Has to be an antinode. And any closed end has to be a node. If there's an open end, that has to be an antinode. If there's a closed end, that has to be a node. So in this case, this has to be an antinode, and this has to be an antinode also, because it's an open end. You understand? Open ends, like in a string. When you had a string, when you plug the string like that, this is fixed, that's fixed. That's why they were nodes. And the middle was an antinode. Whereas when you have an open end is a free end. The vibration can happen freely. Whereas when it bounces back, it forms the node automatically there. So what's the simplest way you can set up a wave over here with one antinode there and one node right there is this. Now remember, it's a longitudinal wave, you won't be able to see it with your eyes. It's made up of compressions and expansions. So this is a compression area and that's an expansion area. But I'm just drawing it for you to understand. So this is the basic, this is called the fundamental. Or the first? Resonance. First resonance, first harmonic, they're all the same terminology. First harmonic. So what is the length of the tube is L. The length of the tube is L. How many wavelengths are accommodated here? How many wavelengths are there from here to here? You should be able to say this. Between antinode and node. 1/4. So L is lambda over 4. So what is lambda then? 4L. Now the first frequency that you're going to be hearing, which is this. The first frequency that you're hearing is velocity over lambda, which is velocity over 4L. So the first frequency is V over 4L. That is the frequency that you're hearing. When I did this, you're hearing this frequency. And can we do some calculations on this? Yes, of course. What is capital V standing for? Velocity of what? Of sound.
Waves.
What waves? Sound waves.
Yeah.
So what is going down here and coming back is sound waves. What's the speed of sound at this temperature? Roughly 340 meters per second. Now the length of this tube, I already measured it. The length of the tube inside is 4.5 centimeters. The length of the tube inside is 4.5 centimeters. So can you put that down here? 4 times, what do you put for length? 0.045. You have to put it in meters. So what's the frequency coming out? What's the first harmonic, first resonance, fundamental? What's the frequency? Calculated. How much?
0.18.
Oh, you have to put this in parentheses. Put this in parentheses. That's a very common calculation mistake, so be careful of that. How much?
1,916.
1,888. Yeah, approximately 1,888 hertz is what you heard just now. Now, if you want to see whether that was the frequency, I'm going to set up the frequency on this one. I'll set up 1800 and approximately this. That one. Does it match up?
Yes.
Pretty close. So you can see the sound that is coming out from here. Sound that's coming from here is the fundamental, and according to calculation, it comes out perfectly right, 1888. The same tube can sound overtones, right? The same way, this also can sound overtones. The same tube can sound overtones. Let's look at the first fundamental. Okay, let's complete this one first. This is a second harmonic. This has to be an antinode, and that has to be a node. So what is the best way to set up the second resonance over here? You will have one extra node. So this is the next possible way of setting up. This is the next possible way of setting up a standing wave. Now what is the length equal to? How many wavelengths is this?
2.
How many wavelengths is that? This is a quarter. This is another quarter. 3 quarters. That's 3 quarters. So lambda is 4L over 3. Lambda is 4L over 3. So therefore, frequency F2 is V over 4L over 3. So the F2 is 3F1. F2 is 3F1. Can you see that? So the first overtone is going to be 3 times this frequency. So if I blow this, that's 1888. 3 times that is going to be our next possible overtone, which is difficult for me to blow. So you can get overtones on this, like this. The next one that you're going to get, here there is 1 node, now you have 2 nodes. How many wavelengths is this? How many wavelengths is that? 0? How many? 5. 5 quarter wavelengths. That's a quarter, 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 quarter. And so lambda is 4L over 5. So if you substitute that, frequency F3 is V over 4L over 5, which is 5 times V over 4L, which is 5F1. So what do you understand from here? That the overtones are jumping odd multiples. You see it? What do you think is the next overtone? 7F1. So you can write down this whole statement. Overtones are odd multiples of fundamental. The overtones in a closed tube, the odd multiples of fundamental. Now coming to the open tube. This has to be an antinode, this is another antinode, so the node comes right in the middle. The node comes right in the middle. How many wavelengths is this? L equal to? 1/2. So lambda is 2L. Therefore, frequency F1 is V over 2L. Have you seen this before?
Yes.
Yes.
In strings, that's what you get. In fact, you get overtones here that are exactly the same like the strings. Look, the second one is going to be like this. The second one is going to be having 2 notes. Here's 1 node, here's 2 nodes. The next one will have 3 nodes. This one has a frequency of F2, which is 2F1. You can work through it the same way as we have done it. And the next one will be 3F1. It's very, very same. It's almost the same thing, except that in a string, what are the ends? Nodes. In the middle will be? And now it's just the opposite. Extremes are antinodes and middle is node. I'll show you how the overtones sound. Now this is an open tube. It's open here, open here. So if I blow, I'll get the fundamental, right? But if I blow faster, I may be able to get this one, which is the second one. And little fast, but I'm not going to blow, I'm going to spin it. So if I spin it like that, that's a fundamental. First overtone. Second overtone. Third overtone. So how many overtones did I got 4 resonances, right? Fundamental. First overtone, second overtone, third overtone. You want to try it?